Hello.
Good morning.
Morning.
Hi, good morning.
Good morning. Hi.
Before we start, can I ask a few doubts?
Okay.
I'm audible, right?
Yeah.
Yes.
Okay. For this year's GSOC 2025 project, I wanted to ask what exactly are we aiming? Like last year we have already implemented some part of it, and this year we are continuing the project. So do we have to enhance last year's part and make the conversation space and work on the issues that are currently open on the GitHub repository, or only the conversation space and the issues? Because I was documenting my proposal and having my research and like some kind of experimentation that I was going on with. But I just want to make sure I'm not going on the wrong path.
Well, I don't know. I don't think we have that many open issues in the repository. So, like, if you go to last year's, what is that?
There are 5 issues. I'll just read them out to you. Issue number 60 is to add a conversation space, which is to simulate stack or like IRC or something. Then we have issue number 61, which is adding engagement metrics based on the conversation space. Then we have integrate RAG within conversation space and GitHub discussion. We also have new issue, like we have to create a issue creator agent to allow dynamic creation of new issues during simulation. And we have collaboration algorithm for multiple agents on a single issue.
All right. Well, those are actually follow-up issues from last year's projects. So you don't have to address those. You could, if you want to. You can pick a specific set of issues and address them in your application, but you don't have to. I think it would be more useful to kind of follow up on what was done last year. It doesn't have to be on specific issues. But last year we did the large language model, agent-based model hybrid model or project, and then some work with multi-agent reinforcement learning. So one of those two, or combining those, or whatever, is probably the way to go. We have a repository. I mean, you know what the issues are, so you know where the repository is. And that repository then has the work from last year. So just try to, I think probably the best way to do that would to do your proposal is to just follow up from last year's work and figure out a way forward. And the issues in the issue in the issue list are merely follow-up things from last year. I usually make people do that because there are things that they didn't complete. There are always things you don't complete. And so to make those clear what those are. And those might serve as technical challenges. They might just be things that are not necessarily relevant to what you want to do. So.
Okay. And any guidelines on what I should specifically include in my proposal?
So, I mean, you need a timeline. So going through from, I guess space it out to like a 12-week program or however long the normal period is. And then figure out for each week what unit of work you're going to do or how much work you're going to do for each week. And then figure out, like, if I run into problems, how do I get around those problems? Do I do some other task while I'm waiting for something to happen, or what? So the schedule or the timeline is very important, and then having some description of what you're going to do is important as well.
Okay. And regarding the project specifically, anything?
What do you mean? Like, well, yeah, how what you want to do fits into the project. I think that's a good way to.
Okay. Thank you.
You're welcome. So it looks like we have Jesse and Morgan and Vidhi and Shyam. So welcome. So anything anyone wanted to mention before we get started? It looks like Jesse's here, and he had mentioned that he's just going to listen in for now. How about Morgan?
Super busy week. I'm just trying to think what news potentially came from that. We're going to be moving. Did I say last week that we're going to be moving the lab to a new space? So
No.
this is exciting in terms of having dedicated space. In terms of full control over this, like 4,500 square feet. And yeah, I think in the first couple months there'll be a good number of people coming through, hopefully interested in funding the build out that we would need for the, so it's one to reach the BSL2 kind of facilities level where we can do mammalian cell culture work, but organoid work really requires a whole new set of equipment that's all basically built inside an incubator. Or, very, very, very specialized equipment that's built inside, that is all housed in the incubators so that you can just keep everything going and maintained and fed, all in temperature controlled. And again, to also reduce you having to move things around. So hopefully more hands off. So that's I think that's our big news. These guys bought a 16-story tower in downtown San Francisco, and so we get a bio floor and a neuro floor.
Oh wow!
But I've been pushing for the neuro floor to be neurobio.
Right.
And the neuro floor to be, when they talk about neurotech, I think they don't understand that most of the valuation in neurotech is going to brain implant companies, right?
Right.
So that's one reason why it's just like with organoid culture, you can actually have a kind of tissue-facing technological development.
Right.
And you can do all of this without animals.
Right.
And which, given our position in the city, is probably, it's doable, but it's, an animal facility is like a whole larger, it's infrastructure, it's people who are just working the animal colonies. and I kind of like the funding story around just let's replace animal testing with organoid culture, and look at med tech in terms of kind of broader technologies. But it's exciting. Definitely going to be a real work in progress for the first couple months. It's a former WeWork building, so the inside's really kind of built out nicely.
Okay.
But anyway, there was definitely good meetings. Well, oh, sorry. Then the brain-inspired. So Paul Middlebrooks.
Yeah.
Is the brain-inspired host who's now affiliated with the transmitter.
Okay.
I believe the Simons Foundation funded neuro magazine, neuro blog.
Yeah.
What do we call? What is Quanta?
Yeah.
There's no physical magazine. He started a and I've got the here. He started the complexity.
Oh yeah, the complex world.
I forget what he called it. The complexity group.
Right.
So they're doing a regular journal club around the Krakauer complexity papers.
Yeah.
And they started with the Latka 52 paper. Anyway, I getting proposals in this week. I was not able to read the paper, but I jumped in on I listened in, and it was it was a nice conversation. A lot of people. It's cool that people like Kevin Mitchell were there. Discussing the paper, and it looks like a really interesting group. So they started their own. It's got it's new, another Discord. Can we please stop starting these? And they'll be deciding, how often they meet soon. I think he was kind of pitching every 2 weeks, but we'll see what people say. But the 4-volume, they got plenty of papers to pick from.
Oh yeah.
Yeah. I think that was. Anyway, I'll try and think of other things as we go.
Okay, sounds great. Thank you. Shyam would like to speak, so unmute. And what would you like to talk about?
It's related to the GSOC project only. I've texted both of the mentors, you, Bradley, and Jesse too. Told that started working on my proposal and I want a review over it. I sent it yesterday, and I was wondering if you've had time to go over it, and maybe you could give me a couple pointers on what you'd like me to elaborate more on, or where you'd like me to put some more effort on. And if you'd also like me to send it over the GSOC channel in the main Slack, I could do that too.
I did see the message, so I'll look into it this weekend and see.
Okay. Sounds great.
Yeah.
So, do I send it over the GSOC channel too, in case Morgan would want to take a look at it? And the other...
I mean, if you want to message him directly, you can. I don't know if he wants to
do
that, but yeah, I mean, it's I have it, yeah, so you don't need to put it in a GSOC channel.
Okay.
Yeah.
Okay, sounds good.
Yeah. All right. Yeah. So that's great. Thank you, Shyam. Okay. So let's see. We'll start with. We'll start off with talking about some new YouTube content on our YouTube channel. So we have our Orthogonal Research and Education Lab YouTube channel. This is a screenshot from my mobile YouTube app, and we have 2 videos here. Developmental Neurosimulation and Interference-Diffusion Pattern Formation, which is about a 30-minute talk that I kind of developed from another talk that I put in the DevaWorm channel. So in the DevaWorm channel, there's a talk on interactive morphogenesis. And so this is kind of a follow-up to that, but focusing more on some of the agent-based stuff that we're doing in developmental neurosimulation. So it's one of these talks where I kind of develop an idea. I've been doing these I did one of these about a year and 3 months ago, where I talked, it was kind of the outcome of a lot of our stuff in cognition futures and cybernetics group. So this is another one of those talks. It's just kind of wide ranging and covers a lot of ground, but it's going to be kind of the basis for future work. So there's that video. And then there's this other video, which is going to be the presentation at the Embodied Intelligence Workshop in 2 weeks. So I'll be presenting at the Embodied Intelligence Workshop on April 2nd, and that will be on this talk, Phylogenetic Models of Embodied Agents. So this is about a 10-minute talk where I go through sort of the phylogenetic view of cognition, and I give a phylogenetic analysis of Bradenburg vehicles, and I talk a lot about our developmental neurosimulation paradigm and some aspects of embodiment having to do with sort of the, I guess I'm calling it the eco-devo approach to embodiment and embodied agents. So this is a nice talk. Go through that if you're interested. A lot of interesting things there, a lot of developing work. So Embodied Intelligence Conference is coming up in 2 weeks, and then we have other things going on this summer. So that's an update on that. Also, we had a DevaWorm meeting this week where I talked about syncytial cells and the C. elegans lineage tree. So I gave a presentation on that. Basically, the idea is that, if you have, if you're familiar with muscle cells, that muscle cells are these large cells that are multinucleated. And those multinucleated cells come from the syncytial, or this process of forming a syncytium, which is where you have all of these nuclei in a single cell body. And you see this in Drosophila development, but you also see it in C. elegans with C. elegans muscle, but also in different structures such as the pharynx and the germline. So you see this again and again in C. elegans, and then the question is, where does that fit into the lineage tree? So I presented a couple of papers that talk about the biophysics of syncytial cells, sort of the process of forming syncytial cells, and then this aspect of fitting it into the lineage tree. So I don't know where that's going in. That's something that someone in the group was interested in, and we kind of talked. I prepared some materials for it. So the meeting number 11 is on the DevaWorm YouTube channel. It's a different YouTube channel, but we have their weekly meetings, and that's weekly meeting 11 for 2025. Okay, so the next thing I'd like to talk about is following up on our data science ML Slack channel. So if you're in our Slack, you know that we have our Slack channels, we have different topical channels. And the thing that's been the most active in the last week or so has been the data science ML channel, where we've been following up from some of the things, our discussions on large language models and reasoning. And so that's this collection of things here. So this is the first thing. I think this was posted in the channel. This is an archive paper it's called Learning to Collaborate by Grouping, a consensus-oriented strategy for multi-agent reinforcement learning. So this is a multi-agent reinforcement learning. So the abstract reads, multi-agent systems require effective coordination between groups and individuals to achieve common goals. So this is relevant to the things that we're going to be doing in GSOC, perhaps, where we've been working on this multi-agent reinforcement learning model of open source communities. So, multi-agent systems are usually something like a system where you have a number of agents maybe working collectively on problems, maybe competing, maybe just kind of existing in the same social group, or maybe in a tissue in a biological simulation. So these multi-agent systems can be quite diverse and have a lot of aspects to them that are basically complexity. So they require effective coordination. You have individuals coordinating on their own, you have groups coordinating, and they have to achieve common goals. However, current multi-agent reinforcement learning, or MARL methods, primarily focus on improving individual policies and do not adequately address group-level policies. So this is where you have these multi-agent reinforcement learning algorithms, and the idea is that you're focusing on cooperation from the individual level. So individual agents all have to sort of implement the same policy to coordinate their activities, but there is this aspect of group level policies that we can exploit, and that's maybe more to the point in terms of fostering effective collaborations. So group level policies, would be like, how does, what are the sort of the hallmarks of the group, thinking about individuals in the group as opposed to individuals pursuing common goals and then forming a group sort of ad hoc. So this focus on individual policies leads to weak cooperation, as you might expect, because individuals always have different objectives and they can fall in and out of the group. And you can think of any strong group versus a group that's sort of ad hoc. An ad hoc group just kind of has members that come and go, and there isn't a lot of strong cooperation there because there's no incentive. Whereas a very strongly reinforced group, it's it reinforces its boundaries, and people have a reason to stay in the group long term. So you get stronger cooperation there. So there are different ways we can play with group level policies to get this sort of stronger cooperation. To address this issue, we propose a novel consensus-oriented strategy, or COS, that emphasizes group and individual policies simultaneously. So again, we don't want to throw out the individual policies, but we also don't want to ignore the group policies. And so a good way to do this is to have sort of a emphasis on both simultaneously. So this is where we're getting this consensus-oriented strategy. Specifically, COS comprises two main components. Comprises two main components. A, which is the vector quantized group consensus module, which extracts discrete latent embeddings that represent the stable and discriminative group consensus. So you have this group consensus where you have a bunch of agents that are kind of finding this set of solutions and kind of figuring out what that is. And then B, the group consensus oriented strategy, which integrates the group policy using a hypernet and the individual policies using the group consensus. So you have this consensus oriented strategy, which basically takes that group policy and integrates it with individual policies and then figures out what the group consensus. So it's different ways of figuring out the group consensus, and then implementing both of those strategies promotes coordination at both the group and individual levels. So there are a lot of kind of theories of group behavior in groups. So if you look at like we were talking about swarm intelligence a couple weeks ago, you can think about swarms as being the products of individual organisms or individual agents that kind of cooperate in a very passive sense. In other words, they all kind of pursue the same goals, and they form these structures that are sort of weakly emergent, but nevertheless there's still these groups that are stable. But you can also have these, you can also think of swarm intelligence as a group level phenomenon. So if it's a group level phenomenon, the agents will do things to further the survival of the swarm. So they're actually making their decisions directly in terms of how to maintain and reinforce the swarm. So this is kind of another way to think about this. Through empirical experiments on cooperative navigation tasks with both discrete and continuous spaces, as well as Google Research Football, we demonstrate that COS outperforms state-of-the-art Merle algorithms and achieves better collaboration, thus providing a promising solution for achieving effective coordination in multi-agent systems. So they talk about where you can use multi-agent systems as a means to improve performance in applications such as multiplayer games, traffic signal control, and sensor networks. And you can model these as multi-agent systems where a team of agents perform a shared task to reach a common goal. So people have looked at multi-agent reinforcement learning as a solution to this. Of course, people have used swarm intelligence as a solution to this. But, neither of those necessarily address both the individual imperatives and the group imperatives. So, there have been other methods that have been proposed for this. Approaches such as ROMA and ROAD, which are acronyms, focus on task decomposition and specialize the agent associated with the role to resolve a certain subtask. LDSA learns dynamic subtask assignments, which can dynamically group agents of similar abilities into the same subtask. So the problem there is that you have this you have to kind of rely on your understanding of the group, or rather the agent's understanding of the group, to sort of understand or to achieve this level of performance. So you have to understand the group as this sort of structure with different, it has to be very tightly coordinated, especially in terms of what's to be done to maintain it. So you have to have these tasks and subtasks, and you really have to decompose different aspects of group behavior. And so sometimes that's not easy to sort of unpack, especially if you have a newly formed group or you have a group that's not very well defined. Having that kind of top-down approach isn't necessarily easy or viable in some cases. So on the one hand, group representations are not well constrained and vulnerable to dynamic changes from the environment or policy training. So when the group changes its dynamics, you can't use that kind of policy, or you can't really rely on those sorts of group representations anymore. On the other hand, the above methods rarely consider extracting a higher level policy guidance from the natural properties of groups, which are these subtasks. So good teamwork often requires a good division of labor, forward-looking guidance to specialize in a certain subtask, and rational individual decision-making. So if we think about, like we were talking about ant colonies when we were talking about swarm intelligence, and in ant colonies, we have a very strong division of labor. We have these collective structures, and there's a strong division of labor, say like in ant colonies, where they do certain tasks, and sometimes those are to the exclusion of doing any other tasks. So in a case like that, it may be very easy to decompose group behavior. But if you think about a bird flock, it may not be so easy, because the birds in a bird flock, you're just using that flock as sort of an expedient structure to travel, to achieve coordination and so forth. So if you think about this in terms of multi-agent reinforcement learning, that group representation is important. And if you go from different, if you take into account different types of groups, your application of multi-agent reinforcement learning will be variable in terms of its efficacy. So it may work very well on something like an ant colony, but not so well on a bird flock. So they propose their approach. They use a couple of pieces of sort of technical work here. First, we use the vector quantized variational autoencoder, or VQVAE, to extract the group consensus embedding, which captures a shared objective that agents in the same group should pursue, and is essential for promoting effective teamwork. So they use this autoencoder to build this representation in latent space. Then we perform the policy learning from 2 levels. So they have these 2 levels. At the higher level, we propose using a hypernetwork architecture to transform group consensus embeddings into a group level set of decisions from global and long-term perspective. So you think about like what the group, the imperatives of the group are, not just as an expedient structure, but as this sort of longer-term structure, but also thinking about how those things differ from the individual. So that's at the higher level. And then at the lower level, we utilize the group consensus embedding as the context prompt to augment the observation to make the individual and refine policies. So they use this group consensus to inform the individual policies that are pursued for individual agents. The combination of these 2 policies guarantees the foresight and precision of the decision-making progress. And so this is just kind of talking about their methodology, some of the things they have representation learning defined. So the representations for observations, actions, or underlying messages are widely studied in MARL. So this is in multi-agent reinforcement learning. Some works, and they give some examples, use bisimulation metrics to extract the latent embeddings from observations. These other 2 references attempt to learn action representations to assist multi-agent policy learning. These references to these 2 references represent underlying messages to conduct effective communication in MAS. There are also some works that use the variational autoencoder to encode the trajectory message to make representation more knowledgeable. So they're using this VQVAE approach, this variational autoencoder, to maintain a quantized hidden space to extractable space and distinguishable group consensus embeddings to associate a more powerful strategy. Okay, so this vector quantized variational autoencoder is described here, and it's there. And this is a figure showing this schematic where you have the vector quantized group consensus. You plug it into an autoencoder. You have this group codebook. You have this history decoder, and then this group consensus embedding, which leads us to the group consensus policy and the group guided policy. Okay. So I think that's enough on that paper. That was one of the papers in our channel. I think it has a lot of relevance to a lot of the things we've been talking about with multi-agent reinforcement learning, swarm intelligence, etc. And it's interesting to see what people are doing and trying to get at that individual group distinction that people have been trying to get at in a number of different areas of theory, like from evolutionary theory to psychological theory, etc., etc. So it's kind of interesting to see that. This is another paper here. This is also from the archive. This is called MicroVQA, a multimodal reasoning benchmark for microscopy-based scientific research. So we were talking a little bit about the large language model scientists or the AI scientists. A couple of weeks ago, we were kind of talking about how reasoning in large language models requires hypothesis formation or hypothesis generation, and then kind of dealing with that as a system. So this is where they're using microscopy data as the input, and they're trying to build this workflow where you can, have this sort of visual understanding, this hypothesis generation, and then this experimental proposal. So you're trying to form sort of experiments based on hypotheses that result from observations, basically. So this figure 1 is a scientific experimentation workflow that drives discovery. Researchers analyze experiments, develop hypotheses, and design further experiments to test their ideas. We released MicroVQA, a visual question answering, or VQA, benchmark to test these three tasks in the context of biological microscopy. So each of these 1,042 samples is created by a biology expert and transformed into a multiple choice question. So this is basically the pipe, or the workflow. So the first part is expert visual understanding. And so you want to develop this sort of perception ability. So the question is, what is unusual about the result? So the system is presented with these microscopy images, and the imperative is to find the things that are unusual about the image. So, you can do like feature selection, which is one way to analyze images. Another way to analyze images is to ask what's unusual about the result, but to ask this in terms of specific questions. So this relies, of course, on labeled data. You have to have labels on this. And one of the questions here is, how is the sepin localized within the endoplasmic reticulum? So you have the endoplasmic reticulum, and you're looking at the sepin, and you're looking at how it's localized. And you're trying to answer that question and maybe identify edge cases or anomalies. The second question here is, do cells treated with BAFF-A1 on this left-hand side express more P26 compared to the control, which is on the right-hand side? So a lot of times, you'll have experiments that generate a control versus a treatment. So you want to find the difference between the treatment and the control. So those are the kinds of things that perception involves. It involves finding anomalies or finding unusual results with a guided question, or it has to be a specific question. It can't just be find anomalies, because that generates a lot of false positives, as you might imagine. So definitely fits into the sort of the philosophy of science, that is, you're answering very guided questions. They say like science is about the questions. And so this is answering some of these questions at the level of perception. The second is hypothesis generation. So instead of asking what is unusual about the result, you might ask, why does this happen in my experiment? And so this is assessment instead of perception. And so this also revolves around some questions. The first one is, which mechanism might explain why ASLV particles show signs of merging in a cryo-EM image? So this is where you see this, you have this cryo-EM image, you know that it's a certain type of image, and then you know that like there's this phenomena in the image, it's not an artifact. So it might be artifactual, it might be some biological phenomenon. So you have to think about the mechanisms that might explain this thing in the image. And again, it could be an artifact, it could be just kind of chance, but it also could be something that's mechanistic in the biology. The second question is, which glial cell is likely responsible for this abnormal reticular fiber pattern? So you see this pattern here, you get this from the perception stage. You might ask, this seems kind of like it might be a question you ask under perception, but you're actually asking a question about the glial cells themselves, not to explain the pattern, but to ask which things are responsible for this result. So this is, again, where this image is evaluated in terms of potential hypotheses. So you generate hypotheses, and then finally you get to this experimental proposal. So how do you test that hypothesis? And so then that goes from assessment to action. So then that requires the system to give a set of experiments to answer some of these questions. So the first question is, what experiment could you perform to test if CCMB1 protein levels relate to cell cycle stages in human A431 cells? So again, what experiments could you perform? Not, mechanisms or, what's unusual about a result. So this is just kind of breaking this down into these stages. that kind of lead to different experiments that can be tested. So that's kind of where we are with that. And again, it's, this is supposed to be a high throughput system where you have a lot of images coming in, and then you're generating a lot of hypotheses, and you're generating a lot of experiments, which might be done, say, with a robot in a wet lab, and it can do thousands of experiments, and you end up with this sort of set of results that are then can be evaluated by an expert human. So this is kind of goes over this multimodal, they're kind of using these multimodal large language models. And so despite recent advances in the area of MLLMs for AI-assisted research, existing multimodal reasoning benchmarks only target up to college-level difficulty, while research-level benchmarks emphasize lower-level perception, falling short of the complex multimodal reasoning needed for scientific discovery. So to bridge this gap, we introduce MicroVQA, which is a visual question and answering benchmark designed to assess 3 reasoning capabilities vital in research workflows: expert image understanding, hypothesis generation, and experiment proposal. So those are the 3 that they identify here. And so they go through this system and kind of thinking about benchmarking. So benchmarking on state-of-the-art MLLMs reveal a peak performance of 53%. Models with smaller large language models only slightly underperform top models, suggesting that language-based reasoning is less challenging than multimodal reasoning. So this is interesting. If you're doing language-based reasoning, it's actually less challenging than the sort of multimodal reasoning. And then tuning with scientific articles enhances performance. Expert analysis of chain of thought responses shows that perception errors are the most frequent, followed by knowledge errors, and then overgeneralization errors. So again, this is this sort of chain of thought response where you have these perception errors, like these false positives that are picked up in the perception stage, and then knowledge errors, which is like an error in kind of interpreting that perception, and then overgeneralization errors, which is where you're overgeneralizing in the second step, and it affects the third step. These insights highlight the challenges of multimodal scientific reasoning, showing MicroVQA as a valuable resource advancing AI-driven biomedical research. So they have MicroVQA available on Huggingface, and then the project is also in a GitHub repository. So the GitHub repository is here. This is the paper with code. The code is here in this repository. And it kind of, I guess you can clone it and use it for your own purposes. Okay, I don't know if you wanted to stop here and ask or answer some questions. Have a question answering session here.
I mean, I love this, it's, I don't know if this should be in the datasci-ML or the, whatever we want to call the AI for science.
Oh, yeah.
Kind of, because again, it's certainly trying to distill, like they said, like they're trying to distill research level, kind of reasonings, right?
Yeah.
It's not reasoning, it's reasonings that humans would have from these things. Anyway.
Okay.
We need more advanced benchmarks.
Yeah. Okay. this is an article by Melanie Mitchell in Science. This is, I think, from this week. It is from this week. So this is, now we covered some of her blog posts in a prior meeting a couple weeks ago, talking about reasoning in AI, in large language models. So this is where she has this article in Science. It's just kind of, I guess, an opinion piece, but it's, kind of following up on those blog posts. So this is called Artificial Intelligence Learns to Reason. So it starts with this statement: Julia has 2 sisters and 1 brother. How many sisters does her brother Martin have? Okay, so that's the puzzle. Now, it may seem obvious, but of course, it probably will not be since you posed the question. Solving this tiny puzzle requires a bit of thinking. You might mentally picture the family of 3 girls and 1 boy, and then realize that the boy has 3 sisters. Or you might figure out a more general rule. Any boy in the family will have 1 more sister than any girl. In other words, the answer to such a puzzle isn't something you immediately know, like Paris is the capital of France. It requires reasoning, a central feature of human intelligence, and one that large language models like GPT-4, for all their impressive behavior, struggle with. I gave this puzzle several times in the most recent version of GPT-4, which is 4.0, and it gave me the wrong answer each time, asserting that Martin had 2 sisters. Indeed, several systematic studies have shown that GPT-4 and similar models lack abilities for robust reasoning, limiting their usefulness in many domains. Prompting tricks such as adding "let's think step by step" to the end of a query to encourage better reasoning can improve LLM's problem-solving abilities in some cases, but such tricks haven't worked well enough to turn these systems into robust reasoners. To remedy this, many of the top artificial intelligence companies have recently created new kinds of AI systems, often called large reasoning models. I think we talked about that. That was Sarah who had mentioned that, I think, last week. And so that is a new tool. She was talking about the ones that Meta was developing, but I guess this is a more general trend in the area. Large reasoning models are specially trained to perform certain types of reasoning. These include OpenAI's O1 and O3 models, Anthropic's Claude with extended thinking mode, Google's Gemini 2.0, Flash Thinking Experimental, and the Chinese company DeepSeek's R1 model. Okay, so those are examples of these kind of large reasoning models. If you give an LRM a puzzle like the one above, it will generate a so-called chain of thought, natural language statements describing a plausible sounding reasoning process in a step-by-step fashion. So this chain of thought is the thing that it's generating instead of just an answer. And so what is that better, or is that, at least it gives us sort of this transparent output. So natural language statements describing a plausible sounding reasoning process in a step-by-step fashion describes a sort of chain of thought approach. For example, I gave the sisters puzzle to OpenAI's O1 model. Unlike GPT-4o, the O1 model gives me its chain of thought to arrive at a correct answer. So its chain of thought is as follows. Number 1, Julia has 2 sisters. That means there are 3 girls in total. Julia plus 2 more. Julia also has 1 brother named Martin. Altogether, there are 4 siblings, 3 girls and 1 boy, Martin. From Martin's perspective, his sisters are all 3 of the girls, Julia and her 2 sisters. Therefore, Martin has 3 sisters. Okay, so that's 5 steps, and it's kind of going through and it's trying to figure out the answer from all the available information and sort of an inference as well. This sounds very much like human thinking out loud, and indeed O1 and other LRMs are trained on many examples of human-generated chains of thought. Being able to generate such reasoning steps has enabled LRMs to reach new performance heights on difficult science, math, and coding benchmarks. For example, OpenAI reported that its O1 model placed in the top 500 students in the U.S. in a qualifier for the U.S. Math Olympiad and exceeded the accuracy of PhD scientists on a benchmark of physics, biology, and chemistry problems. Other LRMs have attained similar benchmark performances. Some companies are betting big on LRMs, being the basis for AI assistants that are commercially lucrative. OpenAI, for example, has released its best LRMs and its associated deep research tool to subscribers paying $200 per month, and is said to be considering charging up to $20,000 per month for reasoning models that can carry out PhD level research, whatever that is. This is defined by these kind of reasoning models. But some researchers are questioning all the excitement over LRMs and asking if these models, as one headline put it, are really thinking and reasoning or just pretending to. That is, does their chain of thought training enable them to reason in a general and robust way, or are they succeeding on certain narrowly defined benchmarks by merely mimicking the human reasoning they were trained on? I'll say more about these questions later, but first I'll sketch out how these models work and how they are trained. So this is kind of, this is just kind of a general model of how these things work. So the different models have different ways that they implement them, but so an LRM is built on top of a pre-trained base model, a large language model such as GPT-4o. In the case of DeepSeek, the base model is their own pre-trained large language model called V3. These base models have been trained on huge amounts of human-generated text, where the training objective is to predict the next token in a text sequence, so like a typical large language model. The base model is then post-trained, that is further trained but with a different objective, to specifically generate chains of thought such as ones that O1 generated for the Sisters puzzle. So I think we had the diagram last week of the different post-training methodologies that are used in different models. So it's basically where you train the model and then you post-train it using a different objective to generate these chains of thought. After this special training, when given a problem, the LRM does not generate tokens one at a time, but generates entire chains of thought. So it no longer generates single tokens in sequence. It's generating kind of these thoughts in sequence and then putting them together as this sort of reasoning chain. Such chains of thought can be really long. Unlike, say, GPT-4o, which generates a relatively small number of tokens one at a time, when given a problem to solve, models like O1 can generate hundreds of thousands of chain of thought steps, sometimes totaling hundreds of thousands of generated tokens, making up the chain of thought steps, most of which are not revealed to the user. And because customers using these models at a large scale are charged by the token, this can get quite expensive. Thus, an LRM does substantially more computation than a large language model to generate an answer. So this computation might involve generating many different possible chains of thought, using another AI model to rate each one and returning the one with the highest rating, or doing a more sophisticated kind of search through possibilities, akin to the look-ahead search that chess or Go playing programs do to figure out a good move. So I like this. This is interesting that they're kind of comparing these chain of thought models to these sort of the chess playing models that we were doing with good old-fashioned AI or GoFi, where you would have these look-ahead search tables. You try to figure out every possible move going forward. When using a model such as O1, these computations happen behind the scenes. The user sees only a summary of the chain of thought steps generated. So to accomplish all this, the post-training of LRMs typically use two machine learning methods: supervised learning and reinforcement learning. So this is where we were talking about last week. We had this table where we had the different models, the different large language models, and then we had this sort of emphasis on reinforcement learning in the reasoning step or the post-training step. And so this is why they're using reinforcement learning, because you have the supervised learning where you're kind of giving it some sort of supervision as to what the correct chain of thought might be, and then this reinforcement learning, which reinforces the correct answers. So supervised learning might involve training the LRM on human-generated reasoning steps created by highly paid human experts, as PhDs, that they say, it's PhD level reasoning. It's because you're using highly paid human experts to generate reasoning steps as the supervision, or on chains of thought generated by another AI model, where each step is graded by humans and yet another AI model. And then it's AI models all the way down, and human experts all the way down as well. Reinforcement learning, by contrast, an unsupervised method, or reinforcement learning is, by contrast, an unsupervised method, in which the LRM itself generates an entire set of reasoning steps leading to an answer. And the model is rewarded only for getting the right answer, and for putting the reasoning steps in the right format for human readability, such as numbering them sequentially or putting them in some framework to interpret. The power of reinforcement learning over huge numbers of trials is that the model can learn which kinds of steps work and which do not, even though it is not given any expensive supervised feedback about the quality of the steps. So the 2025 Turing Award was awarded to 2 researchers who have helped develop the basic reinforcement learning methods that are now used to train LRMs. So that's interesting. So there's been a substantial debate in the AI community of whether LRMs are genuinely reasoning or merely mimicking the kinds of human reasoning that is in the pre-training or post-training data. So one industry blog called O1 the first example of a model with true general reasoning capabilities. Others were more skeptical. Philosopher Shannon Valor called LRM's chain of thought processes a kind of meta-mimicry. That is, these systems generate plausible sounding reasoning traces that mimic the human thinking out loud sequences they have been trained on, but don't necessarily perform robust general problem solving. So that's those are 2 perspectives. There's some people who think that these are true general reasoning capabilities. There are people that say, well, it's kind of this ersatz reasoning that resembles reasoning, but it's not problem solving in any sense. But of course, it's not clear what genuinely reasoning even means. Reasoning itself is an umbrella term for many different types of cognitive problem solving processes. Humans use a multiplicity of strategies, including relying on memorized steps, specific heuristics, such as rules of thumb that we use for kind of good enough solutions, analogies to past solutions, and sometimes even genuine deductive logic. So it's a grab bag of things that we use for reasoning. It's not just this sort of logic one type, like logical deduction, or it's not just listing out a set of steps and walking through them as sort of this sort of, constraints, set of constraints. So, it's really kind of reasoning. If you give it a clear example or a very simple example, it might do very well, but if you give it a more convoluted example, it might not, because you need to bring other different types of strategies to bear on it. So in the world of LRMs, the term reasoning seems to be equated with generating plausible sounding natural language steps to solving a problem, and the extent to which this provides general interpretable problem solving abilities is still an open question. So this goes on a little bit more, but basically that's the idea of this article. So
Yeah, it's it's a good summary of her. Well, I mean, it's an overview. Just one thing. Sarah was talking about large concept models.
Oh, okay.
She talked about doing a presentation on large concept models.
Okay.
And that something akin to sentences being tokens or something like that.
Okay.
Like yeah. Where this was definitely focused on, you know, why there's been such a proliferation of posts in datasci-ML,
Yeah.
which is this you know, like certainly kicked off by DeepSeek. Not that they kicked off this set of models, but when they're you know, much smaller team produced a kind of like an O1 competitor,
Right.
with such modest resources and training resources that yeah. But you know, as usual, Melanie keeps it, or at least as you know, as like we've said, or you know, this is my weekly like. All these people talking about these models have $1 trillion reason to lie about them.
Yeah.
You know, and or you know, if scientists have certain incentives to, you know, gloss over problems in papers, these guys again have empires built.
Right.
You know, empires are at stake for these people, and you know, again, it always, you know, just think about the Chris Fry, the modal AI guy. Just, you know, at the end of the day, this comes down to, yeah, that's like these are the last experts we can pay to solve problems and create training data sets for us, right?
Yeah.
It's like you know, yeah, PhDs we can try, and just makes me also think of the Steve Pantadosi, who's the
Pantadosi.
Berkeley, yeah. You know, that language is for communication, not for thought.
Yeah.
Right. And you know, I get, you know, I get syllogisms and their power, or you know, like their utility, but yeah, just seems very much like our reliance on the tools that we're actually using to try and explain our reasoning to each other, you know,
Yeah.
as opposed to it being how reasoning is done.
So you're describing something, but you're not actually engaging in it. Yeah.
Yeah. Yeah. As well as like, you know, how, I mean, there's, I mean, an old, I don't know, I believe it's a religious saying, you know, that he who tastes knows. But, you know, the funny thing that you have when you try to explain a taste or explain a smell, where you're just like, I don't have words for this.
Yeah.
You know, and it's not, yeah. And it kind of, it somewhat gets at like, we're not trying, you know, again, it's not just that language is communication, but like language is built up for communication about those things that we have reasons to communicate about.
Right.
Right? Because I can just be like, oh, you don't get that smell? Here's the soup I'm you know, like, smell this, you know, like, and anyway, it's and just one final thought on that is somebody we had a meeting event last night at the biolab, and somebody was asking about I forget exactly their example, but it was something like why do people recommend, and including great thinkers, that you engage in some task when you want to think about a problem, like going out and doing some sort of mindless task, or going for a walk, or one of these things. And it kind of came back to that particular point, which is that you if you really want to think, you kind of need to shut up.
Yeah.
It's so giving yourself something to do, giving yourself something to keep your embodiment busy.
Right.
Is yeah. Anyway, but I posted, I think, in random I'm trying to think of the Gail Verquois. So this is one of the scikit-learn core developers,
Right.
and I think he was just responding to Melanie's post, or was just like, whenever I want to demonstrate how dumb a LLM is, I just ask it to play tic-tac-toe.
Oh yeah.
Something, and yeah. Anyway, these are these are incredible artifacts.
Right.
I mean, it's like when you think of the complexity taken to create this matrix, if you will, right? It's got incredible structure. And the people have been posting this week about the Huggingface connections between models. Did I not post this?
I'm not sure.
So just a really interesting visualization of the connections between these models, but which is that which is to say, like, one of them is not just an incredibly complex artifact, but we've been making these these many complex artifacts, and an entire kind of an entire industry around analyzing and trying to understand what are these complex artifacts that we've now made.
Yeah.
But how much are they actually reasoning, and how do we even get at that is a much more profound question. I mean, other than doing mechanical Turk for PhDs, right?
Yeah. So this is charting and navigating Huggingface Model Atlas. So this is analyzing Huggingface, I guess.
Yeah.
So this is stable diffusion versus llama. The Model Atlas visualizes models as nodes in a graph. This is llama. This is stable diffusion, and kind of looking at how they usually do these maps of literature. You have a bunch of papers looking at where they kind of fit into the literature. So we have this atlas here where we have llama models, stable diffusion models, and then these different categories: adapter, fine-tune, quantization, merge, unknown, and root. So you see that the root models are here, and then they have all these forks, which then have these different attributes, some are fine-tuned, some are adapters, some are quantized models, some are unknown models. So the figure shows that the top 30 most downloaded models in the Stable Diffusion and Llama regions. Node size reflects cumulative monthly downloads, and color denotes the transformation type relative to the parent model. So this is where the color coding comes in. Please zoom in to see the detailed model trajectories. We observe that the Llama region has more complex structure and a wider diversity of transformation techniques compared to Stable Diffusion. Note that node position is optimized for clarity and does directly reflect distance between model weights. So I don't know if this Model Atlas demo does anything here. Let's see. Oh, this is, okay, the interactive version. So this is, yeah, so you can click on some of these. Let's see if we can zoom in on them. All right, so this kind of zooms in on specific connections here. Yeah, then just describes the name of the fork here. This is, okay, that's fine tuning. This is an adapter model. And then this is this is an unknown model. Let me zoom back out to find the root model. Here it is. This is Meta's Llama model 3.8b, and then you have these different forks, and you have Black Forest Labs Flux 1, which is a root model, and you have all these forks here. So this is really cool if you're looking for, if you're looking at a root model and you're looking for different versions of it, and it kind of guides you right to where that is. So yeah.
It's still a bit of an art project, but it's absolutely still beautiful.
Yeah.
I mean, like art project in the sense of, as they said, like these distances aren't relevant,
right?
Yeah, but still, I mean, again, remarkable in terms of the amount of work. And again, I would love to focus, or more like the continual AI, like how much, like we're not looking for kind of counterfactual information. Who's like, what are the deficits that are coming from fine tuning? Better characterization of the deficits that come from fine tuning, and
yeah, it's definitely in the spirit of a lot of citation networks where you don't really have a strong set of quantitative principles. It's just kind of like visualizing things, and so it's very much that art project aspect of it.
Pretty.
Yeah. All right, so this is something else that was posted in datasci-ML. This is Introduction to Flow Matching and Diffusion Models. This is an MIT class where they kind of go over this these different types of diffusion models of flow matching and everything.
And this was shared. I mean, I was just passing on what was shared by the guy who started Medarc.
Okay.
Which I forget exactly what Medarc technically represents, but it's the online community that develops particular machine models for a lot of kind of, I guess medical imaging. Just not sure what the ARC necessarily is an acronym for.
Yeah.
But in particular, what they're known for is the mind's eye model, which is that fMRI of, that kind of like fMRI decoding of, is it natural scenes or movies? Anyway, certainly one of the groups that I look to just as a kind of like open science collective. It's just a group that formed online, kind of under this person, to tackle things like that.
Yeah.
And sorry, I'm just saying something. But yeah, thought it might be useful.
Yeah. So this is a nice course outline. They start with flow and diffusion models, talking about generative models, stochastic and ordinary differential equations, and then sampling from flow and diffusion models. Then they talk about constructing a training target, training flow and diffusion models, flow matching, score matching, various approaches to diffusion models, building an image generator. They actually have a lecture in generative robotics, which is really kind of interesting. Large behavior models, diffusion models for robotics. I'm interested in the large behavior models. I don't know what that is. Are you familiar with that?
Large behavior model. Do you think it's like sort of like robotics?
Well, yeah, it's in a robotics kind of thing, but I don't know.
Oh, okay.
I've never heard of large behavior models.
It just kind of reminds me of that. What did they call it? Like X something. Anyway, but it's just like being able to do very large, like a very generalist policy for like a lot of different embedding. I mean, a lot of different embodiments in terms of robotics. I don't know. Let me look. Right. let me stop guessing.
If we can't figure it out from searching, then we can invent something. Yeah, large behavior models.
Oh, large behavior models. Oh, well, according to Google, it's the next evolution in AI.
Well, you do get the ad, the ad version.
That's from Forbes.
Yeah, well, yeah.
Toyota Research Institute. Let me see who's got something here. Yeah, multimodal. Yeah. I mean, they're also talking about like, I mean, again, these robotic models have the same kind of, proliferation and complexity as the atlas we just looked at. In the sense of, how much they can, you can demonstrate a behavior, like if you just film yourself doing some task, how, like how the model can can copy your behavior.
Yeah.
Which is kind of by definition already kind of like one of these visual models. It's like definitely including visual. But I wonder how much of these are still based on. Well, they say they just try to extract get past the marketing speak here, because it's just like they so want to call this the an absolute breakthrough, and yet these are all from last year.
Yeah. So where is it this year? Yeah.
It seems like people trying to
make it a thing, but it's not a thing.
Try to make it a thing, and they're all from a very tightly grouped set of, you can also imagine that this was kind of like one press release, but then made it into like 10 blog posts, so they're all like November 20th, 2024. As well as just how just bad Google's search is these days as well, right? Wait, why am I using Google? Am I using Google? No, I'm using DuckDuckGo here.
Oh, wow.
No, let's see. Anyway, I'll see if there's anything that we can post about this.
Okay, yeah. Let me go back here. There's a lot of stuff here. There's even generative protein design. So, there's a lot of stuff with respect to diffusion models and flow matching and all these things. This is something that maybe we could get into a little bit more in subsequent meetings. I might try to put together some stuff for next week on, kind of understanding diffusion models and understanding some aspects of those. But anyways, so then there's this last thing. This is actually the class in more detail, an introduction to flow matching and diffusion models, and it kind of talks about some of these things. So this is for the introduction, talking about the course structure. Generative modeling is sampling. Flow and diffusion models, going over those more in detail. And again, I don't want to get into this week, but we can get into this later. Constructing the training target, conditional marginal probability path, conditional marginal vector fields, and conditional marginal score functions, then training the generative model through flow matching, score matching, and then a guide to the diffusion model literature, building an image generator, and then a reminder on probability theory, and a proof of the Fokker-Planck equation. So this is all kind of provided as this resource. So that's what's going on in our data science ML channel. Any questions or comments about that? Anything from Vidhi or Shyam? Did you have any thoughts about this or questions?
Not many questions actually, it's fine. But I'll try sending more papers this week or something.
Okay, that's great.
Yeah, so the first time I'm hearing about flow matching and diffusion models, so I don't really have a lot to say either.
Yeah, no problem. Yeah. All right.
I'll post about MedArc too.
Yeah.
Just it's a good group to learn from. They've got a pretty active Discord. Not that we need to be on more Discords and Slacks.
Yet another Discord, yeah. So I'm going to get into a set of papers here. This is a category I'm calling Intelligence in Biological Natural Systems. We've talked a little bit about intelligence and kind of the definitional problems with intelligence, and then I want to get into some things having to do with biological systems, natural systems, and kind of thinking about that. So, that's a link. Morgan just posted a link to MedArc AI. Okay. So let me go back to this. So this is a paper from Network Neuroscience. This is called Linking Fast and Slow. So there's this idea of thinking fast and slow. I think it's Kahneman who proposed this. And this is linking fast and slow. So this is the case for generative models. Carl Friston is on the author list.
And Peter Zeidman's now head of SPM development.
Okay.
so he's, as Carl's moved to run the theoretical neurobiology group, I believe Zeidman's the successor to the analysis group.
Oh, okay. Yeah.
Yeah. I mean, this is neuroimaging stuff.
Right. So this is kind of thinking about this idea of thinking fast and slow as like in terms of these neuronal networks that we can build from neuroimaging data. So let's go over the abstract. A pervasive challenge in neuroscience is testing whether neural connectivity changes over time due to specific causes, such as stimuli, events, or clinical interventions. So this is something where you need to look at neural connectivity and how it changes. So you have to establish some sort of causality as opposed to just observing changes and interpreting them as something, you have a certain likelihood that it could be many things or one thing, but you have to establish a sort of causality to really say whether, it's due to some specific stimulus or some clinical intervention. Recent hardware innovations in falling data storage costs enable longer, more naturalistic neuronal recordings. And so again, we're getting better recordings, more recordings, and so this imperative is stronger than ever. The implicit opportunity for understanding the self-organized brain calls for new analysis methods that link temporal scales. So this is where we're getting these kind of continuous recordings, we're getting longer recordings in these naturalistic settings, and it's no longer kind of like where you have, you're testing things with a fixation cross and then you're getting people to clear their minds, or so you think, and then you're getting a recording of a discrete task that you're presenting over and over, and you can average over those things. Instead, you're getting this kind of naturalistic data where you need to think about multiple temporal scales. So there's an interesting parallel here with continuous learning and how you're not evaluating things on like a specific, very focused task. It's actually where you're trying to analyze behavior over, maybe in some context over a range of tasks. The implicit opportunity, okay. So these temporal scales range from the order of milliseconds, over which neuronal dynamics evolve, to the order of minutes, days, or even years, over which experimental observations unfold. So you have these multiple time scales. You have, seconds where you get, or milliseconds, where you get the neural dynamics for, say, observing some stimulus. We have ERPs that kind of describe these different things in the brain that happen when you're exposed to a specific stimulus, but then putting that in the larger context of minutes, days, and years, where you have things embedded in time. So you have these events that are embedded in time, and you have these long-term performance issues in the brain. So if I give you a stimulus and it's repeated over many minutes, if I just do this continually, if I have like a bell that rings continuously over time, can I observe not only the sort of response to that stimulus, can I also observe some sort of memory mechanism, memory encoding, or can I observe some sort of large-scale change in attentional capacity or whatever? So there's a lot here that's really interesting in terms of uncovering different mechanisms in the brain. And of course that affects the connectivity of a neural network because you have network changes that accompany that. This review article demonstrates how hierarchical generative models and Bayesian inference help to characterize neuronal activity across different time scales. So again, they're the good old Bayesian inference and then these hierarchical generative models. And this is some, tools that we're using to sort of characterize this neuronal activity. Crucially, these methods go beyond describing statistical associations among observations and enable inference about underlying mechanisms. We offer an overview of fundamental concepts in state-space modeling and suggest a taxonomy for these methods. Additionally, we introduce key mathematical principles that underscore a separation of temporal scales, such as the slaving principle, and review Bayesian methods that are being used to test hypotheses about the brain with multiscale data. We hope that this review will serve as a useful primer or experimental and computational neuroscientists on the state-of-the-art and current directions of travel in the complex systems modeling literature. So this is where they kind of give this call for thinking about these cortical circuitries at different timescales. And so, we can look at seizures in our understanding of seizures to see how this is, immediately useful. So seizures sort of evolve in different parts of the brain, and there are these cascades of electrical activity. And to understand seizures and their onset, you need this sort of continuous data and this understanding of continual cognition. So, how does a seizure, say, spread versus, how does it remain localized? And so the electrical activity remains localized. It's not a seizure, but if it spreads out in this sort of avalanche model, then it's, of course, a seizure. So you have this sort of itinerancy of cortical circuitry parameters over seconds to minutes, and there are a bunch of references here. In naturalistic experiments, researchers study the dynamics of the freely behaving brain in exchange with its environment on the scale of minutes to hours. So this is in where naturalistic experiments, allow us to look at some of this freely behaving, what happens in the brain when you're allowed to explore and not focus on a specific task, but focus on a number of tasks and not necessarily in a focused way. So this is, where you're doing this, and of course, not only does your behavior evolve, but your neural dynamics evolve as well. On a larger time scale, studying the progression of Alzheimer's disease requires accounting for processes evolving over months, years, or even decades. In these examples, a challenge is to understand how slow and fast components interact. In other words, how slowly changing variables shape the evolution of rapidly changing ones, and how the latter reciprocally influences the former. This is the citation Ellis, Noble, and O'Connor. So this is the citation here. We'll get to that in a minute. But basically, you have these different types of components in this continual behavior paradigm. You have things that evolve fast or maybe repetitive and predictable, and then you have things that evolve more slowly and maybe are nonlinear in their response. And so there are all sorts of different things that we need to kind of think about, all different sorts of dynamics, all different sorts of phenomena at different time scales. So we need a statistical framework to evaluate hypotheses when empirical observations span multiple temporal scales, when the hypotheses are framed on a different time scale from that of observations. So we might have a hypothesis that says, we think that the neural dynamics do this over time, and there's we have to make an observation of that, and we have to kind of figure out what the signature is that can support or falsify our hypothesis. Quantitatively comparing the evidence for hypotheses amounts to building generative models and comparing their ability to predict the data in terms of model evidence, such as marginal likelihood. Modeling multiple temporal scales affords the potential to better predict future observations. So this is where we want to generate different types of models to generate different hypotheses and test those hypotheses. So this is where generative modeling comes in. This review is based on the overarching idea that evaluating hypotheses with multiscale time series can be systematically addressed by constructing hierarchical models, where each level of the hierarchy accounts for a different temporal scale. So this is again where we have milliseconds, minutes, hours, and we have so many milliseconds in a minute, in a minute, so many milliseconds in an hour. And so we can look at things at the scale of milliseconds and then relate that to what's happening on an hourly basis. And this is the kind of hierarchical scale you need because there are different processes happening at different temporal scales. Like, for example, if you're repeatedly exposed to a stimulus, the response to that stimulus from exposure to exposure is on one time scale, and then, say, a memory encoding mechanism is present at another time scale. And so they ask a question here: how can hierarchical models be used to capture changes in neural connectivity at different temporal scales? And what is the mathematical justification for their use? How to evaluate the evidence for competing hierarchical models in order to address neuroscientific hypotheses or make modeling decisions. For example, which temporal scale should be modeled. So we need to figure out kind of what our hypotheses are, and then what processes do we want to model to sort of address those hypotheses. And then, then build that into a model of neural connectivity. So, they're kind of talking about, so what they'll do in this review is think about how we model the dynamics of time series data at a single time scale, then separate time scales with mathematical models, then introduce a Bayesian statistical method to evaluate the quality of multiscale models, and then conclude with this empirical example from epilepsy research. So they kind of get into some concepts here. So when we're talking about dynamics, we're talking about different types of patterns that we want to see from, get out of these time series. So when we get a time series, of course, time series give us dynamics. They give us this sort of dependent data over time, or with respect to time. So each time point is dependent on the prior time point. So this is different than an experiment where you sort of average over observations. Each observation is considered to be independent. So you can do things like do, t-tests or build models that are based on the sort of IID data or independently distributed data. In continual cognition or in dynamical cognition, we have this different set of affairs, which is that each prior time point is, each time point is dependent on its prior time point. So you can build these kind of dynamical models where you can look at different phenomena of sort of the evolution of a time series. So we can look at these different things here. We can look at these flows and trajectories in a state space. So the state space represents sort of all possible trajectories that result from a series of observations. You map this out by drawing this trajectory that kind of goes out, and this is x1 versus x2. So this is sort of where you can measure fluctuations, you can measure repeated patterns and draw them out like this. You can also look at trajectories in the time domain. So instead of comparing x1 and x2 in a bivariate space, you can compare it to time. So x1 evolves over time, x2 evolves over time. And you can see that, in the state space, you have this sort of attractor basin that forms. You can see that here. And that's because you're getting this sort of repeated behavior when comparing x1 and x2. So you get these sort of dynamics that are, you get these periods where there's a maximum and then a minimum and so on and so forth. They fluctuate over time. And you're not capturing time here, but you're capturing the interaction between these two variables. In the sort of IAD data that we usually use in neuroscience, the interactions are bad. But in this case, interactions are good. They allow you to see these kind of evolutionary trajectories. So again, we can do this, we can plot this against two interacting variables. We can plot this over time. We get these oscillations over time, or what is more accurately described as sort of a flux over time. Then you have bifurcations where you have trajectories that bifurcate due to some event. So you have maybe some common trajectory that gets bifurcated by some historical event, like a perturbation if I'm exposed to some noise in the environment, or if an onset of a seizure occurs. And you can measure this out with these kind of tools. Looking at these bifurcations, and there's some sort of critical value that describes when a bifurcation is expected to happen. So these are all, there are a lot of predictive tools from complexity theory, like the Hough bifurcation, which allows you to use parameters to predict or model these sorts of phenomena in systems. And then we have multi-stability, which of course is where you can compare two interacting variables, and instead of having one attractor basin, you have multiple attractor basins or multiple points where the system is stable over time. So, again, we have like a place where the system tends to settle. We have maybe like one mean for that. I don't want to call it a mean, but in general, that's what it is. It's a mean behavior. And multi-stability of multiple mean behaviors in different regions of the phase space. And so, the trajectory might visit one of these stable points and then visit another stable point and then fluctuate back and forth between these stable points with an intermediate of instability where there's a potential for change, large-scale change to the system. So I want to look up this paper here we'd mentioned before. Ellis, Noble, and O'Connor. Okay, so there's this paper, Ellis, Noble, and O'Connor. This is top-down causation, an integrating theme within and across the sciences. That's phrased as a question. This is from Interface Focus in 2012. So this is the paper here, top-down causation, an integrating theme within and across the sciences. So this is by George Ellis, Dennis Noble, and Timothy O'Connor. And then this abstract reads, this is actually, I think, talking about the special issue. I'm not familiar. This is a special issue on top-down causation. So there are more papers to this. But it kind of talks about the special issue. This issue of the journal is focused on top-down or downward causation. The words in this title, however, already raise or beg many questions. Causation can be of many kinds. They form our ways of ordering our scientific understanding of the world, all the way from the reductive concept of cause as elementary objects exerting forces on each other, through to the more holistic concept of attractors towards which whole systems move, into adaptive selection taking place in the context of an ecosystem. As for top and down, in the present scientific context, these are clearly metaphorical. So top down just means like if you go to that top hierarchical layer, there's an effect that goes downward in the system. So, if you think about your body is like the top of a hierarchy, which includes, organs, tissues, cells, and then, with the contents within a cell. So anything I put my body through, if I experience a traumatic injury, I can damage my tissues, I can damage my cells, I can have blunt force trauma, and they all happen at different hierarchical scales. But that perturbation is imposed from the top down. You can also think about this in terms of social organization, where you have organizations where you have like a leader at the top of the hierarchy, and they impose rules that then the systems underneath them have to adhere to. And sometimes the mapping isn't very clear, but that's what happens in these kind of hierarchies, is that top-down things are sometimes inefficient, sometimes they're, don't allow for certain types of complexity to evolve and so forth. So there's a metaphoric aspect to this, but basically, we think of top-down as like this imposition on a system. And so in the present scientific context, these are clearly metaphorical, as some of the articles in this issue of the journal make clear. Do we therefore know what we are talking about? So this is a set of papers by philosophers and scientists. And then they kind of talk about this idea of emergence and top-down, causation. So this is really I was kind of hoping for a more explicative paper, but this is fine. They just talk about top-down causation, and so they actually ask if it's an integrating theme within and across the sciences, where you have different sciences where they use this concept, but they have to map it to different things, and this is good in terms of thinking about neuronal networks and intelligence, because you have these things that happen at these large scales and kind of have to be sort of imposed upon smaller scales and smaller processes. So then they say there's a roadmap for future research, which we won't talk about so much, but is kind of relevant to this paper, because I think the idea here is that you're connecting this to emergence and emergent complexity. And if we go back to our paper, a lot of our methods here sort of implicitly involve emergent complexity, because a lot of these trajectories over time will eventually form these larger scale patterns which emerge from smaller scale interactions. So if you have interactions between like a stimulus and a brain response, and that's repeated over time, you can get this large scale phenomenon of like adaptation or memory consolidation, or maybe a seizure if you're in the right context. But they actually do give some interesting methodological points here. The first is that they're evaluating hypotheses with hierarchical models of multiscale time series. And so a mathematical model that they described earlier in the paper specifies a hypothesis about how the measured data were generated. Arbitrating between hypotheses entails specifying a suitable set of models and having the statistical machinery in place to compare their evidence. This selection sets out recent developments in Bayesian statistical methods, which are proving useful in neuroimaging and related fields that deal with multi-scale time series data and dynamic models. So they kind of go through this. They have this very Bayesian-oriented approach where they talk about the probability of one event affecting another event. And of course, that's what we're talking about with respect to dependency with respect to time. So, it lends itself to this Bayesian approach where you can say, what is the prior thing that happened and how does that factor into the likelihood of something else happening? So you can analyze these trajectories with Bayesian techniques and Bayesian descriptions. And then, of course, talking more about hierarchical models and inverting them. So to recap, each level of a hierarchical model has parameters that are constrained by the level above. For example, with neuronal recordings, a neural mass model may be used at the first level, so at the lower level, with parameters that encode synaptic connection strengths. So this is a specific type of model people use to look at neuronal recordings, and the parameters are specific to that context, that application of the model of the system. Slow changes in these synaptic parameters over a longer time period, such as seconds or minutes, are described by the second level of the model, with parameters that govern the slow dynamics. So you have two models here. You have a neural mass model, which encodes synaptic connection strengths, but the strengths change over time. So you need a new set of parameters that describe those dynamics of those connection strengths changing. So if you think about it in terms of how those levels are connected, there's some top-down causation in terms of the changes over time affecting a specific instance of synaptic connection strengths. So if I give you a weight matrix of synaptic connection strengths, that results from a snapshot in time of this model, of the lower model. And then the model above it is imposing, its own, that model is imposing itself upon those dynamics. So it's determining those dynamics. Okay, so that's kind of an example of that. And so, yeah, they get into a lot of good stuff in this paper. But I think we'll stop there and go to the next one. So the next one is related to this, and this is by Victor Scherza and Egidio D'Angelo, and this is the quest for multiscale brain modeling. So this is related to what we were talking about in the last paper. This is where we're thinking about the brain at specific scales or specific levels, hierarchical levels. And so we're thinking about things like synaptic connections, long-term synaptic changes, brain regions, and then things that affect the whole brain. And so we have these different levels. We have top-down causation, but we also sometimes have bottom-up causation. So bottom-up causation is where you have things at lower levels that affect things at higher levels. And oftentimes in complex systems, we have a mix of both of them going on at the same time. So we have things coming from top-down and also things coming from bottom-up. A lot of times when we describe emergence, for example, we have this bottom-up causation. So we have the actions of individual agents that contribute to the formation of, say, like a flock or a swarm or some collective, some group. And so, those are, but of course also that group can affect the behavior of individuals. It can constrain the behavior of individuals. It can determine how they're organized, what kinds of rules they follow, and so forth. So this top-down and bottom-up causation is a loop, and it's hard to sort of disentangle that in complex systems, which is why we need to do this sort of multi-scale brain modeling, because analyzing the brain at any one scale of analysis is limiting. We can't necessarily make statements about causality if we don't have these different scales available to us. So that's where this review comes in. The abstract talks about sort of addressing the multi-scale organization of the brain. So the brain is inherently multi-scale. It's not just complex. It has many scales of organization. And it's a challenge because we don't really fully understand a lot of these scales and how they're related. And when we say there's a scale, we basically have to abstract that out of what is basically a complex dynamic organ. So when we say that like synaptic connections are a scale, and we say that things that modulate synaptic connections are another scale, we're making a choice about what the scales are. Those aren't necessarily, there's an inherent property of synaptic connections. We can define them and say, this is a set of synaptic connections, and that is one scale of analysis. And then the things that modulate those synaptic connections are another scale of analysis. But we don't necessarily know, they're not necessarily separable. We don't necessarily know that that's a higher scale or higher order. And so we can't necessarily say a lot about top-down and bottom-up causation in those cases. So in principle, it should be possible to model neurons and its synapses in detail, and then connect them into large neuronal assemblies to explain the relationship between microscopic phenomena, large-scale brain networks, and behavior. So it should be possible to do this. We should be able to get the detail, and then we should be able to kind of neatly separate these out, kind of figure out how they fit together, and then explain this relationship pretty easily. However, it is more difficult to infer neuronal functions from the ensemble measurements, such as those currently obtained with brain activity recordings. So our measurements introduce another layer, another complication in this, which is when we define, say, like a scale, we have measurements that sort of define that scale. In other words, if we have synaptic connections, we have to measure those synaptic connections using weight. That weight then is what? It's kind of describing what's happening at that synaptic connection, but then of course we don't know what that measure, if it's like the only measure available. We might have multiple measures. We might have ensemble measurements, which are a collection of measurements. and kind of how that fits into function. So, this is kind of a harder problem. So, in this article, we consider theories and strategies for combining bottom-up models generated from principles of neuronal biophysics with top-down models based on ensemble representations of network activity and on functional principles. So what they're proposing is that you have these networks, and remember, we're talking about a brain network as our sort of goal, as sort of the top level. And we have all these things that are contained in each node. So every brain network is a series of nodes and edges. The nodes have properties. Sometimes they have properties all the way down. That is, you can have a node that's like a neuron or a neuronal connection. And then there's like a biochemistry of that. And, and that's another layer of analysis. So there are multi-scale aspects of each node. And then the edges, which are the edges of the network, which can be described in multiple ways, and affects how we measure this network and its connectivity. So we have this bottom-up sort of approach where we can take the neuronal units and look at how they're connected together and then make inferences about the network. But of course, if we get the measurement wrong down at the lower level, then that sort of bottom-up approach is flawed. Also, with the top-down approach, if we kind of infer a network from something like a neuronal unit, and our measurement of the neuronal unit isn't exacting or good, then that can also complicate our model. So this is a pretty hard problem, and so they describe a number of integrative approaches that allow us to build effective multi-scale simulation in virtual brains and neurobots or neurorobots, and pave the way to future applications in medicine and information technologies. So in the highlights box here, they talk about multi-scale brain modeling, along with the availability of computational technologies and biomedical data. This is a rapidly growing field, generating an intricate set of strategies, tools, and applications. Data-driven models using biological details at multiple scales to simulate brain activity. So we have data-driven models. We also have task-driven models, which anticipate the functions needed to simulate behavior. So we actually have two different types of models we can use for multi-scale modeling. We can have data-driven models, which really focus on biological details, getting biological data for these different scales, and then simulating what happens in the brain. And then task-driven models, which kind of are behavior-driven, which are driven from specific tasks and looking at how those can be used to simulate behavior. Data-driven models, though, can proceed in either bottom-up or top-down way. So a data-driven model, if it's bottom-up, it usually starts from neuronal and synaptic mechanisms and moves upward towards the brain network. And top-down is where we take the connectomics data or the network data or brain signal recordings from large regions and work downwards towards these neuronal and synaptic mechanisms. And so we can actually go in both directions at once, but then integrating those is a problem. Here we show how the different modeling strategies can be integrated to generate hybrid simulators, allowing to fill gaps in knowledge through principled rules, to uncover hidden parameter values, to generate testable hypotheses guiding future research, and to open new perspectives for artificial intelligence towards personalized medicine and brain digital twins. So the last part is always like marketing, or kind of how this is useful, and but this part kind of talks about the multi-scale aspect of brain modeling. So one interesting thing here is where they talk about this multi-scale problem, which is, of course, how do we build accurate multi-scale models that integrate top-down and bottom-up causality in a well-defined way. So facing the multi-scale problem requires a well-defined strategy based on what are called direct and inverse models. So we have direct models and we have inverse models. because they crucially determine the way in which brain models are generated. Basically, a direct model predicts the effects from knowledge of the causes, whereas an inverse model casts light on the causes given the effects. So we kind of know sort of the causes. I mean, in a direct model, we try to predict the effects from knowledge of the causes. So we try to figure out what the causes are, and then we predict the effects that we should see. So we have any sort of like set of relationships between two things. We can then predict the effects that should be there, and that gives us our model. The inverse model, by contrast, casts light on the causes given the effects. So we look at the effects, and then we try to inversely predict the causes. So it just really depends sometimes on your system, sometimes on what kind of data you have, and so forth. More formally, if one knows the model FP as well as the parameters P, one can directly predict the observable signals, which are the observed signals for the function FP. Inversely, one can determine P or its parameters based on observations, the inverse observations. In brain terms, one needs to correlate the many neuronal activities that generate ensemble network properties with the ensemble signals measured through recording techniques such as MRI, EEG, MEG, and PET. The direct problem is often referred to as the bottom-up modeling strategy because it climbs the complexity scale from elementary causes to ensemble functions, whereas the inverse problem relates to a top-down modeling strategy because it tries to infer the hidden causes of the ensemble observations. As discussed later, modeling can go either way, bottom-up or top-down, and the two strategies can intersect depending on the availability of data and the specific problem under investigation. So this is nice, and it kind of gives a little bit of a primer on how to implement these, how to think about them. So yeah, this is a summary of this. So you have a direct problem versus an inverse problem. You're going from elementary causes, which are, say, like single recordings or cell signals, as they call them, and then you move maybe from the direction of single cell signals to ensemble signals using the direct problem, and the inverse problem is taking the ensemble signals and moving backwards to the single cell signals. So a single cell signal might be like recording of direct, like electrophysiological recording, whereas an ensemble signal might be something like an EEG trace or an fMRI signal, where you're measuring from a number of cells simultaneously and getting a signal that sort of summarizes that. So what they're referring to is the model parameters that allow you to go from one type of model to another. So I think that's enough for that paper. Any questions, comments? And I'm going to talk about a little bit different type of paper next. So I know that Morgan has some opinions about neuroimaging and.
Well, this is my this is my area. I don't think multiscale brain modeling is used in Siri.
Yeah.
But yeah, Victor is is one of the three forces behind the Virtual Brain Project. So this is the big it's his. I mean, it's somewhat directed by him because he's the multiscale physicist.
Yeah.
Or like his advisor was the lasers guy.
Yeah, lasers guy.
I'm blanking on synergistics.
Oh, Haken, Herman Haken.
Thank you. Yes. And anyway, so it's as well as first, I mean,
Yeah.
and Frisman and Zeidman, so it's like you kind of have two competing software projects.
Right.
The London guys are the kind of, well, for certainly some decades have been the preeminent fMRI analysis package.
Mhm.
And thinking, and then expanding to EEG. And, so they were dealing with these new timescales, right? And this also comes out from, the kind of examples that the First and Zeidman paper are having from epilepsy, where you've got potentially grid electrodes in the brain itself, right? And so you could be doing recordings like that, as well as looking at other kinds of fMRI measures, which are hemodynamic, and therefore on, whereas the grids are on a millisecond scale, the hemodynamics are on a second scale, right? Seconds scale, right? And certainly, the hope is that you could potentially, somehow infer from the hemodynamics what you should see if you were recording from the electrodes.
Yeah.
And of course so this is certainly the reason that I've been very happy that I crashed into EEG at a young age from no direction of my own, but just happened into a project that involved high density EEG, and so I got to see brain dynamics at that different temporal scale, right? And so I love these projects. The virtual brain project is very different. I mean, it's funny though, because I think one of yours big, perhaps best funded. I don't know, you never know which of these are passion projects or which just happened to get funded. But his digital twin of epilepsy is the virtual brain project. I think it's the premier virtual brain project. So they both can, they're both looking at it, but from different perspective. I think one reflects, Zeidman's the last author on that paper, but that was very first in approach. I mean, Zeidman's a student of Friston, and so and it comes out in certainly the active inference book, here is all the different the hierarchical Bayesian models that they're talking about, and yours is giving you the physicist version of that,
Right.
I mean, it's but you to some degree, I mean, but they converge, right?
Right.
And so I think it's it just kind of speaks to their different perspectives, but really important. Somebody last night, this is a bio meeting, so this was a person who's coming from like computational chemistry, but trying to do brain modeling that included kind of like synaptic release, vesicle, neurotransmitter release,
Right.
as well as like global brain dynamics,
Right.
and kind of neuroimaging. I think she's more coming from, kind of PET, which is again like a very different time scale, but it's it's really the future brain imaging. I mean, in the kind of like the world in which I was in, is being able to think more about those kinds of multi-level dynamics and inferences. Yeah, great. I sent one of those. I actually sent the years of paper to her.
Okay, good.
the person I met last night was like, hey, you should check. I'd said like, she should look at the Virtual Brain Project, and so that was a nice article about it, or about their philosophy.
Yeah. So we have these two different kind of ways of thinking about it, but they're convergent. Largely, the Bayesian model being a large difference, and there are different ways you can, these aren't the only two ways you can characterize this, because as we get out from neuroimaging, we get to other kinds of systems, especially in biology, like in ecology, or like in other types of physiology, where you're maybe thinking about different types of measurements, or you're thinking about different types of phenomena, affecting. It was intentionally vague about the different forms of causality, because these are theoretical concepts, and they kind of map to different measurements, different systems, how they're defined, how the levels of complexity are defined. So it's really up to the system you're working in, and the conventions of measurement, and the conventions of saying this exists at this scale, this exists at this scale.
Yeah, for sure. And yeah, I mean, sometimes it's like, I mean, I think they might be using causality, but they kind of also just mean like temporal aggregation.
Yeah.
like but the point being that you have a microscale model, and it has, you can determine the macro from the micro, right? But it that could be quite a simple that could be quite a simple averaging, so to speak, or something like that.
So in some formulations of this, the top down sort of serves as constraints, and the bottom up serves as sort of information. So like if you have if you have synaptic connections, and they're going to the next level, to like a network level, they're serving as information for that level. Whereas the network topology, which is the connectivity between cells or neurons, that constrains your synaptic connections, and so you have that relationship, and that's like kind of more of a more of a classic sort of complexity theory approach, where it depends on your system, what you're working in, but you should be able to observe these things across different types of systems. There's an assumption of universality there, that basically this is how it works. You just have to find your system of interest, and you'll find these kinds of dynamics and principles at play.
Right. It's I mean, you can take the kind of like all models are wrong, but some are useful.
Yeah.
But I was thinking about it when you brought this up, like, I mean, especially the first and Zeidman one, right? Which I was just thinking about the kind of like the neuro AI for neuroscience, like they don't just want a a lower level dynamics that explains, that explains the kind of the data that they could collect at the scale they can collect it, right? They want the mechanisms underneath, they hope that they're settling on something that's closer to the actual mechanistic bottom-up models, right? Let me give you an example, and this actually comes from a Zeidman talk like a couple months ago, where he was talking about the SPM 25, and he brought up a tool from San Diego called Hough, which is this kind of like full spectrum EEG modeling package that Bradley Wojtek's group developed.
Yeah.
And Wojtek's group is doing kind of like it's very much doing phenomenology of the power spectrum.
Yeah.
In the sense that like it's not right. So this is your potentially. Even if you're not collapsing across channels, you're getting this power spectrum, and Zeidman was talking about how they want to move to a generative model of the EEG power spectrum, and it's one of these. So you could do that in a couple ways, right? You could do that where you, in a sense, you don't have a spatial model, right?
Mm-hmm.
And kind of again make it kind of like a mixture of distributions that explain, so it's just like you can look at that power spectrum and not in like a Fourier way, but just in a probabilistic distribution way, you could be like, okay, I've got like this distribution that looks like a gamma that has that kind of like power law,
mm-hmm.
like behavior, and then I've got like kind of like a Laplacian at around alpha and then like a smaller one at around beta, that explains the little blips that you usually see in these. But that doesn't, like that is leaving out a lot of information that is probably actually really important just in terms of the cortical sheet, connectivity of the cortical sheet, and to bring up like Wave Club and Earl Miller, like that traveling waves are a thing.
Yeah.
and that a lot of this kind of dynamical systems, just that, and like early, like thinking about early neurophysics models from Australia, which I assume just reflects like one PI that had students or something like that.
Yeah.
But that they were doing a lot of these models where it was assuming the cortex is just a flat sheet, like doing a lot of physicsy things that didn't actually sort of make spatial sense.
Yeah.
But you could, they would have this spatial model that could start to explain, from bottom up. Right. You could start to explain the EEG power spectrum. So this would be like J.J. Wright and Dave Liley and like a bunch of New Zealand anesthesiologists for some reason.
Yeah.
And yeah, it's just again, it's one of these trade-offs, I guess, you have to make in kind of physics modeling, where it's like how like how well can you specify in advance that spatial model, or something like and that's the all models are wrong, some are useful thing, where it's just like, so somebody eventually come along with a more useful model. Anyway, I'm not sure if that rant was helpful, but
it was,
just thinking about something as kind of like easy to derive, but also that is widely used. Like we do all these derived measures off of the human EEG power spectrum. We have no idea what it really. I mean, lots of theories, but no really good solid answers in terms of what is alpha even, right? Which was the original Hans Berger discovery of EEG in the late 20s. Anyway,
right.
Good papers.
Yeah, thanks. Okay, so I think that's it for this week. Thanks for attending, and see you next week.
Take care.
Take care.
Bye.
Thanks. Bye.